Today we're going to start discussing kinematics, particularly in one dimension. So kinematics is the study of motion in physics. And the questions that we're going to be dealing with are questions about how fast, how far, how much time did something take to move, anything associated with the motion of an object. So we're really going to be looking at the study of motion. So before we can start to get into analyzing motion, we need to introduce ourselves to a few different quantities, a few different physical quantities. So and these quantities include displacement, velocity, and acceleration. And the interesting thing, or the thing to note about all three of these quantities, is that each of them is a vector. So they have to be treated in such a way. So let's go through these one by one. And today we're going to focus particularly on displacement and velocity. So I'll start off with displacement. So the displacement, a basic definition for the displacement is the vector difference. It's a vector difference, of course. Between the starting and ending positions of an object. Okay, so once again, one of the important things is that displacement is a vector, and it only depends on the start and the end of a path, starting and ending positions of some path. So imagine that you have an object that is starting from this point right here, and it travels to some ending point via some circuitous path. Could be anything. And we end over here. So the displacement is the vector difference between the end and the start. It has nothing to do with this dashed path that the object takes. Rather, graphically, we can draw the displacement as simply a straight line that connects the starting and the ending points. So displacement is independent of the path. And that is the primary difference between the displacement and the difference between two positions. So the difference that we talk about is usually a scalar quantity that accounts for the path taking. So the distance traveled by this object, of course, is the amount, whatever distance that the object takes along that dashed line path. But the displacement only accounts for the ending and the starting positions. So we could do a really quick example dealing with displacement. And we'll do one where, let's see, you run 20 meters due north, then walk 15 meters at some angle 60 degrees south of east. So I want to know, what is your displacement? All right, so the picture for this problem looks something like this. We start down here at some origin. We walk 20 meters straight north, and then we come back and walk a bit southeast. So that's 15 meters. And we've been given this angle right here, which is 60 degrees. So this is really a vector addition problem. I simply want to add these two vectors together so that I can come up with the resulting displacement, which I'm going to call delta r. All right, the vector difference between the starting and ending positions. So I'm going to take a unique approach to solving this problem. I'm going to break, in order to add two vectors together, as we've learned before, you need to break the vectors up into their components. So in this example, if I set up my coordinate system sort of like I normally would, x and y as such, where x is the east direction and y is the north direction, I can break up my components into their north and east, or my vectors into their north and east components. So I'm going to write down a table that has two columns just to do this really explicitly. And we're going to look at the components of the walking vector. I'm sorry, let's do the run vector first since that's the order. So the run vector and then the walk vector. So we start off by running 20 meters, and we do that straight north. So there's no breaking anything up into components here. The east component of my run vector is 0. So that's really easy. Now if we look at my walking vector, I go 15 meters, but I don't do so either north or east. I go in between. So I need to break this vector up into its components. And the components I'm looking at are the sides of this right triangle right here. And this is the x component of the walking vector, and this is the y component of the walking vector. So the x component is going to be the side that is opposite to this angle, and this angle is 90 minus 60, or 30 degrees. So this component is going to be opposite to my angle. If it's opposite, I'm going to make use of the sine of 30 degrees. Oh, I'm sorry, I'm doing the wrong one. So I'm actually solving for the north component here. This is the north column, so I'm using the side that's adjacent to the angle. So that's going to be the cosine of 30 degrees. And then I notice that I'm going, when I move in my walking leg here, I'm actually going downwards. So I'm going in the south direction, and south is in the opposite to my coordinate system. So that's, I'm going to have to stick a negative sign out in front of this expression. And then in the east direction now, I'm still going east, so it's going to be a positive number. And I'm going to use the sine of the angle to come up with the eastern component. So in order to get my displacement, I just add these two terms together. So I get 20 meters minus 15 meters times the cosine of 30. And if you do that calculation, you should get something like 7 meters. And that should be a positive 7 meters. And then this side, 15 times the sine of 30, that's actually 7.5 meters. So if I write this down in some sort of vector notation, I get delta r is equal to 7.5 meters in the I-hat direction, because east is what I defined as x, plus 7 meters in the j-hat direction. So that's my vector. That's my vector displacement, and I've calculated, and that's a perfectly acceptable answer. But in some cases, I may actually be interested in what is the magnitude of the vector as well as the direction associated with it. So I'm going to redraw my vector delta r. And what I'm really, now what I'm after is, okay, what's the length of this vector given the sides are y and rx? And then also, what is this angle, the angle from the positive x-axis? So to come up with the magnitude of the vector, magnitude of delta r, I use the Pythagorean theorem. That's 7.5 meters squared plus 7 meters squared, and I take the square root. And if you solve for that number, you should get something like 10.3 meters. And then to get the angle, I can choose whichever trig identity I want. I'm going to use the inverse tangent here. And the inverse tangent of this angle is going to be ry divided by rx. So that's 7 meters divided by 7.5. And if you do that, you get something pretty close to 45. I don't know what it exactly is, but because these two numbers are about the same, that should be about 45 degrees. So that's another way to write my vector, is it has a magnitude of 10.3 meters at 45 degrees. In this case, I define theta to be north of east. So there's a pretty straightforward example of doing vector addition to calculate a displacement. And this is actually very similar to an example we did last week, involving more than 2 vectors even, so it might even be easier. So that's the displacement, the vector difference between 2 positions. Now let's move on and talk about the velocity. So velocity is something that we're familiar with, but we're more familiar with the scalar version of velocity, which is actually called the speed. Velocity, unlike speed, is a vector. So I'm beating the vector part of this stuff into your head. And it shows the direction and rate of motion. All right, so I can put that into algebraic form and give you a definition. I'm just going to write down the magnitude. The velocity is equal to the displacement over the time. So this is where we get a rate. A rate of motion refers to some physical quantity divided by time. And if you look at this, we can get the units for the velocity, which are simply meters per second. This displacement is a meter. Displacement is measured in meters and time in seconds in our SI unit system. There's 2 types of velocities that we're going to worry about. Or we're going to consider the average velocity and the instantaneous velocity. So let's talk about those 2 concepts. Start off with the average velocity. So in order to look at the average velocity, let's take a look at a basic example here. In this case, we're going to look at the case of a car that's traveling at some speed. And we'll attach some numbers to this motion. This car is going to move 400 meters from a starting position to an ending position, so we can define some displacement. And it's going to take 16 seconds to complete that motion. So it's going to start at this position, move to the right, 400 meters in 16 seconds. So my average velocity, the average, is simply equal to the displacement divided by time. In other words, if I calculate if my rate displacement is delta x vector, and time is delta t, where delta t just means the elapsed time between 2 points in time, I can calculate the velocity, and that's simply going to be 400 meters per second, or 400 meters divided by 16 seconds. Now, of course, I'm doing a vector, so I want to make sure that I get the direction right, and the direction for velocity is the same as the direction for displacement. So my displacement here is to the right. I've moved from this position to this position, so the vector points to the right, so my velocity is also going to be to the right. And just so that I can complete this, if I solve 400 divided by 16, that's 25 meters per second, again to the right. So that's my average velocity. Now, of course, in this example, it certainly could be that the car could have started from rest. So that means that at any point in the path of this car, at any point in the motion of this car, it could have been moving slower than 25 meters per second, and since it started from rest, at some point it must have also been moving faster than 25 meters per second. This velocity is simply the average over this entire path. It doesn't tell us anything about how fast it was moving at the beginning, or how fast it was moving at the end, or how fast it was moving when it got to this point right here. In order to learn that, to talk about that, we need to talk about something called instantaneous velocity. So the instantaneous velocity looks very similar to the average velocity, and I'm going to write it very similarly, except I'm going to leave off that subscript, except for a subtle difference in how we treat the time. So I'm going to start off with the same equation here, except now I'm going to say, well, really, I'm going to do the same sort of thing. I'm going to calculate my velocity in the same manner, but instead of looking at 16 seconds, I'm going to shorten up that time interval. So, you know, I could cut that down to 8 seconds and maybe look at the first part of the first part of the path. Or I could cut that down to 2 seconds and maybe look at some small section of the path. But if I want the instantaneous velocity, really what I care about is how fast is something moving for a very, very, very small blip of time. In other words, if I let that delta t go all the way to 0, in other words, I'm looking at just a small sliver in time, what my change in position is, that'll tell me my instantaneous velocity. And of course, having taken calculus, you'll recognize this as simply a derivative. The change in position, the derivative of the position with respect to time, is the velocity, is the instantaneous velocity. So at this point, we're just going to leave it at that. This is our fundamental definition for instantaneous velocity. We're going to come back and do an example in a little bit dealing with that. But the important thing to recognize is that in order to get an instantaneous velocity, we need to have position as a function of time, right? Because I can't just, in an example like this, I don't have enough information to figure out the instantaneous velocity. Instead, I need to know position x as a function of time t, so I can take the derivative, either numerically or or analytically. Okay. So, but anyway, for now, let's focus on an example and dealing with the velocity. So let's do another example here. And in this case, we're going to have a police chase. So you are running from the police. And running, I mean driving because you're in a car. At a velocity of v is equal to 8 meters per second east. The police chase at 35 meters per second, also to the east. And then at time t is equal to 0, your position is x is equal to 120 meters, and then the police are at x sub p is equal to 15 meters. So you've got a bit of a head start. All right, so the picture looks something like this. Here's the police car. It's a bit of a boxy thing. And the police car is moving at v sub p, which is 35 meters per second. Up ahead, here you are in your sports car, moving at a bit slower speed, 8 meters per second. And of course, these are velocities, so they're vectors. But you've got a bit of a head start. So this is x, and we'll call this x sub p. So I want to know, when does the police car catch up? All right, so how long does it take for the police car to catch you? But there's sort of a hidden question within this question. So, you know, what I'm really asking, I'm asking about the time, how long does it take? But what I'm really asking is, when, in terms of physical quantities, that's what I'm really asking, when does x sub p equal x? That's the question that I'm really after. Okay, so that tells us a little bit about how to approach this problem. So the way that we can approach this problem is, well, we're given something about velocity, we're giving something about position, and we're looking for something about time. So those quantities are all related by our basic definition of velocity. So right, velocity is equal to displacement over time, at least average velocity is. Okay? Now if I write this down in sort of long form, delta x, that just is really our final position minus our initial position, and then divided by time, because we are always dealing with time durations. So what you notice here is in this form of the equation, I know something about velocity, I know something about my initial position. I want to know something about time, and then there's this, or I'm sorry, I know something, and I know something, I know a little bit of something about my final position. So we can write an equation of this form for both the police car and for your car. So let's write down for your car first. So I'm going to rearrange this equation and solve for the final position. I'm going to solve for the position as a function of time. So x as a function of time is going to be equal to x naught, that's this term, right, which I've moved to the right, and I've moved this to the left-hand side, and this is on the right-hand side, plus v times t, plus the velocity times time. So for your car, what this looks like, x sub t is equal to 120 meters plus the velocity, which is 8 meters per second, times the time, which I'm after, which I don't know. I want to know how long something takes to happen. And I can write down a similar equation for the police car, which is x sub p as a function of time is equal to 15 meters plus 35 meters per second times time. All right, so I have two equations here, and it seems like I have three unknowns. But remember, I said what I'm really after in this question is the amount of time it takes for x to equal x sub p. In other words, I want to know what is t when these two equations equal one another. So if I write that down, 120 meters plus 8 meters per second times t is equal to 15 meters plus 35 meters per second times t. So what I'm after is what time t does this equation hold? And of course, I've got one equation with one unknown, so I can solve this. And we can quickly go through doing that. So if I just solve, solve so that the t's are all on one side and collect the terms, I can factor out my velocity terms. So I get v sub police car minus v times t, 8 meters per second and 15 meters per second. And that's equal to 120 meters minus 15 meters. So that's 105 meters. So what I'm going to get here, if I solve for t, is that 105 meters divided by 35 meters per second minus 8 meters per second. That's equal to t. So if I solve for this, I get t is equal to 3.9 seconds. So that's the amount of time it takes for the police car to catch up with your car. And this answer sort of makes sense because I'm dealing with velocities, with the velocity, the police car's velocity is quite a bit faster than your velocity. So I don't expect it to take very long for the police car to make up that 100 meters or so.